So I work doing carbon dioxide reduction, and it's obviously important in terms of global warming and climate change. And in terms of my research, I can use electrochemistry to convert carbon dioxide back into useful products.
The carbon dioxide is an important heat-trapping greenhouse gas, and its accumulation in the atmosphere results in an increase of the global temperature. Global climate change has already had observable effects on the environment. Worldwide, it's recognized that recycling carbon dioxide to fuels and other high-added biochemicals is a key element towards sustainable low-carbon economy. CO2 recycling will play a vital role in worldwide efforts to limit global warming and will allow us to deliver a fifth of the emission reduction needed by 2050.
So using electrochemistry, we can turn carbon dioxide back into useful products. This is carbon dioxide utilization, and we can turn it into things like methanol, ethanol, and formate. Things like methanol can be used as fuels. Formate is a very important precursor in chemical industries. Ethanol is also another type of fuel. These products are obviously more useful than carbon dioxide, which is very inert, and we have to sequester and put underground if we don't want it to contribute to global warming. So when I'm doing carbon dioxide reduction electrochemically, we have to do it in aqueous electrolyte because that's what provides the protons for the reduction reaction. We obviously have a very large water peak that we don't want to see, so the NMR that we do suppresses that water signal peak without losing all the other little signal peaks around it that we want to see. When I'm doing my electrochemistry, I change the electrolyte in order to get the best reaction conditions, and this affects the NMR spectrum that we get. Bridget and Cecile from the NMR department helped me quite a lot in order to change the parameters of the pulse sequence so that I can get the best quantification, which is the end goal of doing this kind of NMR.